Hello, this is lecture 2 of the mechanism analysis and design, or theory of machines if you like, and we're still talking about the degrees of freedom in linkages, their connotation, what they are used for, and the design aspects of these degrees of freedom. And we have here a simple example. It's I have a 4 by chain here, just link counting number of links 1, giving the number 1 to all the fixed stationary points because they fall in the one ground link. And I have link 2, this link here is link 2, and I have link number 3, which is obviously that's all welded together, give us one like V like looking link pattern. And then I have link number 4 here. This is link number 5, which is a slider, and that's link number 6. So n is equal to 6 in this case. All right. And now when I count my revolute joints, I have a revolute joint here because the angle of side changes. So whenever I have the like angular change, I know that's a revolute joint. I have also another revolute joint here because the angle changes, that's a revolute joint. I have a revolute joint here. I have another one here. I have another one here, and I have one at point A. So when we count those, we get 6 revolute joints. And we have one prismatic joint, which is this one here. That's prismatic joint inside here, signifies the relationship between the slider and link number 6. So don't forget that A slides on 6 or link 5 slides on link 6 if you like. Okay, now if I want to calculate my degrees of freedom and I apply the equation we learned earlier, the equation says F is equal to 3 n minus 1 minus 2 times revolute joints minus 2 times prismatic joints minus the higher pair if we have tried any. Then we have 3 6 minus 1 minus 2 times 6 minus 2 times 1 minus 0 if you like, and then this gives us 1. So that's a single degree of freedom linkage we are dealing with here. So one motor is needed to run it. I can just take a note on the side. One motor is needed to run it. Okay, just simplify. So one motor is needed to run the linkage, and usually I would connect this motor at like the center of or the pivot of the shortest link, because like here link number 2 type thing. So I expect the motor to be connected here, just because normally like the shortest link is expected to be able to do 360 like continuous motion type thing. So you have a motor here, it's continuous motion. Usually you got high speed if you like, low torque, and then the other links in the arrangement will have lower speed, normally be variable like speeds, while the input link, the link it's connected to the motor, will have a constant speed. The other ones will have lower values of speeds, like lower levels, but will be variable, and hence the torque will be magnified. The torque coming from the motor will be low at the link to end where the motor is fitted, and then the torque will be magnified at other links, just like levers do type stuff. So linkages do torque magnification as well, as we'll discover soon in this lecture series. Now I can also say that one parameter is needed to describe the position of any link in the linkage. So I can say, for example, this parameter here, this specific, this is an interesting one, the angle of the link which I expect the motor to be connected to, this angle here, angle phi. Later on I'll be able to calculate the position of any point, for example, like point C, the X and Y of point C here, or any other point, and also the angle of any other link, for example, the angle psi here. I will be able to calculate those values as function of the single parameter, which will be the angle of the link which is attached to the motor. So this later on we'll be able to write the equation, this function of the angle phi. It can be a complicated equation, but nevertheless will be able to, with the knowledge of the value of phi, to calculate corresponding values of the angle psi, for example, type thing. So that's another meaning for the word single degree of freedom, where you have like in a single degree of freedom, like either one motor or one geometric parameter is required to calculate the position of any other of the various points and links in the linkage. All right, let's take another example. Let's example 2. Here I have the number of links in the example. I have already counted, and I did like those numbers encircled. I have 6 of them, so that's 6 links. Review joints here are, so we have a review joint here, another one here, another one here, and another one here, and another one here. So these are all review joints. So 1, 2, 3, that's 5 of them. So R is equal to 5. I have a prismatic joint, which is this one here, and I have one higher pair, which signifies this connection here, type thing. So that's higher pair, just the follower sort of slides on the can type thing. So that's either a point or a line type contact. When we calculate number of degrees of freedom here, I'll be able to get the, okay, let's do it together first. So this will be 3, n minus 1, n being 6, that's 6 minus 1, minus 2 times 5 r, minus 2 times 1 p, minus 1 times 1. Yeah, so this will give me 15 minus 13, that's 2. So that's a 2 degree of freedom linkage, and it makes sense if 2 degree of freedom. Now, so we need 2 motors to drive this linkage. I would imagine, if we think together, what is the meaning of that? Like when we are getting 2 for the first time, like not the first time, we got 2 before, but one of the freedom available, one of the degrees of freedom was extraneous when we dealt with the cam operating a roller forward earlier, like in the maybe previous lecture. But over here we are getting 2, but both of those 2 degrees of freedom are real ones, and I'll explain how in a second. Now if we, okay, so in this case here we have 2 degrees of freedom, and I would say both these 2 degrees are meaningful, and I need 2 motors to run this linkage, and I would say possibly one of the motors would be fitted here. So maybe I'll have a motor here, and where to fit the other motor, I would possibly place the other motor here. So I'll also place another motor here, and I can justify this in a second. I'll be able to justify that for you. So let's assume, for example, that I have decided to fix link number 6. So now let me insert, I'll insert another image here for this link. So insert here, image, and I'll find this link in a second here, linkage, and I'll insert it here. So just placing that will become one thing with the page. So now, so if I decided that this link here is going to be stationary, right? So how many degrees of freedom I'm going to have? So in this case, n, which was 6 before, is going to be only 5. because now link number 6 is the ground type thing, and my revolute joints have been reduced by 1 because this here is not a revolute joint anymore. This is not a revolute joint anymore. That's all one link. So I have now 5. Prismatic is still 1. H is still 1. So when I calculate my degrees of freedom, I get 3. 5 minus 1 minus 2 times 5 minus 2 times 1 minus 1. So I get 3 times 4, I get 12. 3 times 4, 12 minus how many review joints I'm dealing with right now. They are 1, 2, 3, 4. So review joints, in fact, it was 5 before. It is 4 in this case. I'm going to redeem myself here and say I have 4 review joints. So I have R is equal to 4. So this minus 8 minus 2 minus 1. So I have 1. So this is a single degree of freedom. Now what this means is the mechanism still functions, still rotates. I still have my motor here running attached to the cam and running this linkage. But however, when I have managed to fix link number 6, I'm getting a linkage that rotates, meaning that I don't need link number 6 to rotate to be able to run the linkage, to operate the linkage. So if link number 6 rotates, that's another freedom in the linkage that I need to control independently with another source of motion or a prime mover. So now if I go back to my initial linkage you started with here, so if I have motor 1 and motor 2, and I can, with motor 2, if I rotate it at whatever angle, like, I have a time function for this angle, like theta 6 here, right? And I can sort of, together with the angle of this motor here, I can force point B or the slider link number 5 to follow a trajectory that I need to have in my machine. So if I need this specific point to follow a specific trajectory, I need to change this angle here together with this angle here in whatever way that will cause point B to move on a trajectory. Don't forget that if I want this to move on any trajectory, that's quite flexible in this case because point B on the trajectory has X and Y coordinates at 2 degrees of freedom, and my linkage itself has 2 degrees of freedom, being 2 degrees of freedom are in fact theta 2 and theta 6, right? Sort of thing. As I mean, even the case when I fix link number 6, in fact, this is like, just again, imagine you decided to lock the motor of which provides theta 6 for you, sort of thing, at a specific value type thing. So that's you get a single degree of freedom because you decided this motor is going to have a 0 velocity, and so link number 6 becomes stationary or becomes a ground type thing. All right, so let's look at some other interesting examples. Now, here this will be page 12. Example 2. This will be example number 3. So this example here, I'm going to look at a 4-bar chain. Right, and then I'm going to say, okay, I want to calculate degrees of freedom as well in this case. So I'm going to my link. So I think I've done this problem before. So I have 4 links counting from 1 to 4, and I have some revolute joints here. I have 4 revolute joints R, 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 R. So I have 4 revolute joints. Then N is equal to 4. It's something I'm repeating from a previous lecture. R is equal to 4. So my freedom is 3. 4 minus 1 minus 2 times 4, right? Of course, P is equal to 0, H is equal to 0. You can write that, or you can just leave it, doesn't matter. So this will be equal to 1. So single degree of freedom, we understand that we need one motor to rotate or operate the thing, which can be placed here, the shortest link, and also it means that this angle theta 2, I can calculate the angle of any other link, we'll see in future lectures, theta 3 as function of theta 2, and I can calculate theta 4 as function of theta 2. In fact, and any other x and y values can be function of theta 2, my single degree of freedom. So, right, I'm just repeating the definition of single degree of freedom here. The number of parameters required to calculate position of any link or point in the linkage, or the number of motors required to run the linkage type thing. All right. So now I'm going to add something to this specific linkage here. So I'm going to say, here I have, I'm going to have another link. Let's say this link here will be link number 5. So I have link number 2, link number 3, link number 4, link number 1, right? And I'm going to add link number 5. Then once we have done that, I want to calculate degrees of freedom, I'll find that the change is page number 13, okay, 13, and page number 14. Yeah, okay. So now once I've done that, my degrees of freedom will change because, okay, let's look at our n is equal to, in this case, n is equal to 5 because I added just one link. And review joins, let's count them because now we have an interesting situation I want you to pay attention to. So I have a review joint here, I have a review joint here, but over here I have two review joints, and over here I have two review joints. The reason is I have three links connected here in this junction, right? And I have three links connected in this junction here. So normally the number of joints at a junction is equal to the number of links minus 1. So normally the way we think about it is we fix one of the links. We think of one of the links as if it was a stationary link, and then the other links will start moving with respect to that stationary link. And every link moves with it and make some, like, calculates displacement, angular or whatever. This will correspond to one revolute joint. So in fact, I say here R is equal to n minus 1, where n is the number of links at a junction. So that's 3 minus 1 is equal to 2. Same thing at this other end here, right? Okay, so now straight away I can calculate my number of review joints will be equal to 6, and then the freedom then will be 3, 5 minus 1 minus 2 times 6, which will give me 0. So now tells me that this linkage has become a structure now. Once you added this extra link, link number 5, the linkage will not be able to rotate any further. And I can prove this geometrically for you. So let's say I have, okay, I'll just try to prove it simply with some simple drawing here. So I know that this is going to be circular arc here, and this will move on a circular arc there, right? Type thing. So, and I'm going to add link number 5. So if motion, this is link number 5 here. So if motion is going to happen, because we assume all links rigid, So link number 5 is going also to follow a circular motion here about this center, right? Type thing. So now assume motion is going to take place. So we'll find that, for example, if this is point A and now it moves to point A prime, and now I want to find where point, so this was point B, I want to find point B prime. So from R3, with the knowledge of R3, I can draw a circular arc, right, which to intersect this here. And if everything was fine, then without link number 5 added, this would have been the new position of the linkage. This is the new position without link number 5. So if 5 was not added, this would be the situation. But however, link number 5 is actually added, is here. And link number 5 wants to move on this circular arc. All right. So now link number 2 wants to move. Link number 4 here wants to come to this point to move on the red circular arc, but but link number 5 wants to move on the blue circular arc. So this here is R5, this one here is R4, and I would say possibly this one here is R3 type thing. So if you see the discrepancy, so of course now there are two, like link number 4 wants to come here, and link number 5 wants to move on a different arc. So they will never really agree together, and unless you have an elastic, some elasticity in the system, like if link number 5 would be a spring or something like that, right? So that if its length is going to change, but because we have rigid links, so we know that the motion is not possible, and as such, we end up with a structure. So motion is not going to occur at all. So we have that's a 0 degree of freedom linkage, which has become a structure because it's 0 degree of freedom, right? And it makes sense. It's not actually moving. Now, let's now add another link to this. So let's say if I have that, so that's my linkage with link number 5 here. So that's link number 5, and I decided to add link number 6 to it. So that's link number 6. So now, how many degrees of freedom I now have in this arrangement? So let's count those together. I have n is equal to 6 because I have 6 links. R now will be equal to 8 because R is equal to 2 everywhere because I have 3 links at every junction. R is equal to 2, R is equal to 2, meaning that F is equal to 3, 6 minus 1 minus 2 times 8, which is -1. So this is here and is interesting. This is an interesting result, -1. So what does this mean? I understand 0 degrees of freedom means a structure, right? That's not going to move. But what is -1? What does it mean in terms of degrees of freedom? Okay, now it means different things to different people, right? So for example, to a civil engineer, it means we have a structure, but there is a redundancy in it. There is a link that we don't need to cause the linkage to become a structure, which is link number 6, which we added recently. So this link, that it was already a structure, the arrangement, but we added another link. So maybe you do this in reality to achieve, if you like, a level of stiffness you wanted to achieve in your design or something like that. But it's not going to like it's not going to stop, like it's not needed to make a linkage structure or anything like that. So there is some redundancy in the process. And even when civil engineers try to calculate forces in the arrangement or in the structure with this redundancy, they find it difficult to use the statics equation. The sum of forces is equal to zero, and the sum of moments is equal to zero. To calculate the forces or the reactions in the members, in this case, they have to use an extra material-based equation called compatibility equation type thing. So that because in this case they call that the linkage is statically indeterminate the structure is statically indeterminate because of this redundancy, right? This is to a civil engineer trying to calculate the reactions, or a designer in general trying to calculate the reactions in the linkage. They have to use more than the statics, the equations of equilibrium, the statics equation. Now, to an engineer who is going to design and manufacture something like that, they need to think about the -1 figure they got for the degrees of freedom in the following fashion. Right. Now think about the linkage again. When we added link number 5, this link here, we had a linkage that moved before adding link number 5, right? So if we wanted to transform this linkage into a structure, we decided to add link number 5, right? So, and then, remember that the linkage still moved then before we added link number 5. So if we manufactured link number 5 with some error in it, in the length, we could still fit it in the linkage because the linkage was still moving, and we can still actually manipulate the distance between this point here and A and point C, for example, till we get the distance between the 2 points to match whatever we manufactured in terms of length of link number 5, right? So that this was quite possible. But once we fit link number 5 in the linkage, now we have a structure, doesn't move any more. When we are getting link number 6 to fit in this new arrangement, it has to be designed to a high level of accuracy. So we can actually fit it between point here, let's say point A, B, for example, A, B, C, D, and point D, for example. So if link number 6 will come between D and will come between B, it has to be very accurately manufactured to fit between the 2 points, because now at this point in time we have a structure and the distance between the 2 points is already fixed type thing. So now link number 6 has to be, you pay more money to manufacture this specific link, and the fact that it has to be highly machined and highly accurate then is highlighted or signified by the -1 number that we got. So the mobility or the freedom, which is -1 here, to me, it indicates to me or suggests to me that when I'm manufacturing link number 6, I'm going to pay more money. I'm going to specify the manufacturing tolerances on the drawing, so I make sure that the people who are going to machine this for me, they know what they're doing, and then they machine something accurate which I can fit inside the structure. So then the -1 value, this value here, I take this as a wake-up call, something like you need to be alert to some complications that may happen if you don't have the accuracy. Another interesting situation, which is similar to this situation, is when you have, okay, just this is example number 3, maybe another example number 4, example 4 over here. So let's say I have linkage such as this one here, right? So it's parallelogram type linkage, which is a 4-bar linkage as well, with 4 links and 4 W joints also. So that's I have. So this is a single degree of freedom linkage, right? And it's well known. It's like the old steam engine, those trains and things like that. So now, if I decided, so now what I have is this is equal and parallel here, and this is equal and parallel to the other one. Now, what if I decided to insert a link like that? And I tell you, it's still equal and parallel. What is going to happen to this linkage? Is it still going to rotate or not? So that's a question I'm asking you. Now, when we calculate, I mean, based on geometry, you can guess it's going to rotate, right? It's not going to, because this added link number 5, is not different from link number 1 and link number 3, as long as it's still parallel and it is, sort of equal. So now, if I want to calculate let's calculate degrees of freedom. I have 5, and R is equal to 6, right? So you'll find that your degrees of freedom will be equal to 3, 5 minus 1 minus 2 times 6, and you get 0. So you are getting a 0 freedom in this, and you know it is going to move, right? So that's strange because the linkage still moves, right? So we are getting 0, we are getting f equals 0, even though the linkage is functional, right? So this is something we need to think about. So when we get 0 again, we get a degree of freedom that is not expected or does not comply, does not match reality, because in reality we have a single degree of freedom linkage here, and we're getting 0, and then what? So if this mismatch is again a wake-up call for us. This rings a bell for us, and it tells us there is geometric constraint, right? So this geometric constraint, exactly like we had previously here, where link number 6 had to be manufactured to a high level of accuracy, right? Geometric constraint here is like link number 5 has to be exactly parallel and equal to 1 and 3, and any deviation from that, this linkage is not going to function, type thing. So as long as you have so the degree of freedom, the number we get from the degree of freedom calculation is more of a wake-up call. It makes you think what is happening here. So I get a number that I don't expect, then I need to think about it and I need to make the right decision, type thing. Okay, so now we have, just going to say, we have geometric constraint, we have geometric constraints. So 5 has to be exactly parallel and equal, right, to 1 and 3. And any deviation from that, this linkage is not going to function. Again, you have to, when you manufacture that, you pay lots of money just to make sure it's exactly the specific length. And when you fit it, and on link 2 and link 4, you have to make sure you are not going to disturb the parallelism and the linkage at all. So now I'm just saying here that those degrees of freedom, these calculations we do for degrees of freedom is more, it's very useful because it gives us the actual, like, in most cases, straightforward calculations as what's happening and number of motors and stuff. But occasionally it gives us numbers we don't expect. And at this point in time, this is an opportunity for us to stop for a second and think what is needed, what extra constraints I have to deal with here to ensure motion is going to happen, and so on, right? Now, I'm going to touch quickly on the degree of freedom in a special linkage, even though we don't really do special linkages in this course in terms of further analysis, but it's an interesting and simple and easy enough thing to understand when you calculate degrees of freedom of a special linkage. So if you have to, you can, you want to look at so a Stewart platform or Stewart platform, or like a flight simulator or something like that. You're wondering how many degrees of freedom it has, whatever, you will be able to apply an equation and get a number quickly. Right, so let's deal with special linkages. Right, right. So now in space, an object in space has x degrees of freedom. Remember, an object in a plane had only three. Like an object in a plane was in fact a straight line with x and y of it, and the angle of the line with the x-axis would be sufficient to draw the object in a plane. So it was a 3 degree of freedom situation in a plane. But in space, the situation is different, because I mean in space I don't have a line, I have more like a solid object, like 3D object. All right, so this object has a point on the object, would have x, y, z coordinates, correct? And also the center line of this object would have angles with the three axes. So like if I say, okay, let's x, y, and z, and the center line is here, it would have an angle alpha and maybe beta with that, and maybe an angle gamma over here, sort of thing. So it has three angles with the three axes, right? And in fact, these three angles are related together with one equation. So you need only two of the angles to find the third. For example, the equation is called direction cosine equation. So cosine square plus cosine square plus cosine square, the three angles add up to 1. So meaning that if I knew two of the angles, I can simply just calculate the third angle. So the angles give me 2 degrees of freedom. So meaning that the center line itself has 5 degrees of freedom. So center line has 5 degrees of freedom, being what? Being x, y, z of a point, and alpha, and alpha, and what? And I'll just do that, and alpha and beta, right? Angle with x-axis and angle with y-axis, right? However, I said earlier that an object in space has 6 degrees of freedom. Yes, it does, because the object is not the center line. The object is a solid around the center line, and this object, in fact, can even rotate about the center line with another degree of freedom, uh, theta. And hence, an object in space has all the degrees of freedom of the center line, but also it has this ability to rotate about the center line, and hence the object has 6 degrees of freedom. So the object itself, about the center line, because the object is, this is the center line, and the object is, if you rotate a point by an angle theta here, the point will move like that from one position to another. So we'll leave the plane, move to another plane. So the object itself, the object has 6 degrees of freedom, being x, y, z, alpha, beta, and theta, right? Type thing. Okay, so we know that the object in space has 6 degrees of freedom. Now, this number 16, correct? Okay, it is. All right. Now, then if I want to write my equation, right? So the equation now, how will it look like? So the equation, or let's write the equation together. So in the plane, in the plane, I had, okay, in the plane, the equation was 3 n minus 1 minus y, because, okay, I'm going to delete that here. I'm going to write in this and compare the two things together. So I'm going to say this 3 in the plane, because the object in the plane or the line had 3 degrees of freedom. In space it has 6. So go 6 n minus 1. And remember this minus 1, the reason for minus 1, because one of the links was actually stationary. Now go back to the plane. I have every r deducted 2. Why every r deducts 2? Because r allows for 1 degree of freedom, which is rotation. Okay, now so it has to deduct 2 from the 3. In the space, it will have to deduct 5, correct? Same, and 2p, so this will be 5p. Okay, now h will be exactly h, so h will be h here. All right, that's all good so far, except in the space I have 2 joints which I couldn't use in the plane. So these 2 joints I can use in space, or like I'm going to call them special joints, right? So let's just give them a name. One of them is a cylindrical joint, and the other one is the um, the ball and socket joint. The cylindrical joint, if you remember, was simply just a cylinder inside and like a cylindrical sort of, ball, and this was allowed to slide and was allowed to rotate, right? So it has 2 degree of freedom, right? So you expect it to deduct 4, right? Because in the space we have 6 degrees of freedom for an object, right? The other thing here, which was like a, and the reason the cylindrical is special one, by the way, because as it rotates, it takes a point from one plane to another. You see, when it rotates like that, it takes a point from one plane to another type thing, right? Hence, it's a special joint. The other special joint was the ball and socket joint. So it's something like that, again, like that, and it's fixed, let's say here. And so then the center line of it, so this is the center line of it, is very much like the center line we spoke about earlier. Remember, the center line had 5 degrees of freedom, x, y, z, alpha, beta. Okay, now this center line here has 2 degrees of freedom because the end of it is fixed. So x and y and z are fixed at a point, right? So the center point is known, and so it has, if you like, 2 angular degrees of freedom. So the center line has 2 angular degrees of freedom, being what? Being alpha and beta, right? Angles with the x-axis and angle with the y-axis. Okay, but this joint has 3 degrees of freedom. Why? Because also the joint can rotate about the center line with an angle theta. So the joint itself, the ball and socket joint, has 3 degrees of freedom, being what? Being alpha, beta of the center line, and the rotation about on axis type thing. So if I want to incorporate those two equations, two components now in my equation, I'm going to write the equation like that. I'm going to say F is equal to 6n minus 1 minus 5r minus 5p minus, I'm going to, this joint here, I'm going to use C as like a symbol for it. And this joint, like the ball and socket joint, ball and socket, I'm going to use G for it. So minus, then 4 cylindrical minus 3G minus H. The equation becomes something like that in the space. Okay, that's the proper equation. And let's look at an example. So let's take an example. So I'm going to say, okay, let's do one example. All right, so that's example here. Going to talk about something called universal joint in this example. Universal joint, and some people I think call it the cardan joint as well. Cardan joint, and the concept here is to be able, if you have, the concept is you'd have a shaft, right, at one end, and you have a shaft at the other end, and you want, and those shafts are not necessarily parallel, not intersecting, whatever, and you want to like move or transmit the motion from one shaft to the other. So this is where you get to use this specific joint, and it gives us a linkage. So I in between here I use a cross link, right? And all right, so now I have this cross link here, and I have, okay, so this link here. All right, so let's see. I'm going intentionally, I sort of did something here which is not 100% because I want you to make some discoveries in the process. So let's count the number of links we have in this arrangement. So I have, again, my frame is everywhere the one, right? And I have this link number 2. I have the cross link, right? This is link cross link. That's link number 3. I have link number 4, this one here. I have another cross link, link number 5, and I have link number 6, this one here. So n is equal to 6, right? Now I have revolute joints here. So that's a revolute joint R, and I have 3 links here. So I have R is equal to 2 in this arrangement, right? Because I have 3 links together at this junction. Or I can say, for example, there is R between 2 and 3, and between 3, so this is link number 3, don't forget, number 3, and between 3 and 4, there is another R, and same here, and same here. So R is 1, 2, 3, 4, 5, 6, R is equal to 6. So when you calculate F is equal to 6 minus 1 minus 5 times 6, which is 0. So you get 0. So, and which means, like degrees of freedom, meaning, which means that this link is not going to rotate, or this linkage is not going to function, not going to rotate, unless all those shafts are perfectly aligned together, type thing. But this is not the purpose for which the cardan or the universal joint is, is built. In fact, it is built to provide flexibility. So the shafts don't have to be aligned or anything like that. Can be skewed, right? Then, so the actual design of the joint is not what I give you here in this example. In fact, the actual design of the joint is like that. So we have here, we have here, so this link here, and we just insert a prismatic joint here, and we have this link, and we have that link like that. So I have over here. Right. So now when I go back to count, I have link number 1, link number 2, link number 3, link number 4, link number 5, link number 6, link number 7. So now n is equal to 7. And my revolute joints, I have a revolute joint here, I have one here, I have one across, and I have one here, one across, and one here. So I still have 6 revolute joints, but in this time around I have a prismatic joint, which is this one here, and this makes all the difference. When I calculate f now, it is equal to f is equal to 6 and 7 minus 1 minus 5 times r, which is 6, minus 5, which is 6, 5 times 1 prismatic. Okay, so now that's 1. So that's single degree of freedom linkage. And in fact, I can, from, if I know the angle rotated here, theta 2, I'll be able to calculate the angle theta 7 as a function of theta 2, right? It's a single degree of freedom linkage, and it is it's like it's spatial linkage, however, which attach shafts quite skewed and used in transmission of power from the engine in the front to the back of the cars, like where the gear where the differential is, sort of in trucks and things like that. You'll be able to see them if you search, if you Google Cardan joint or universal joint. Okay, so hence it is something like that. All right, so there is a question which is also, just to finish off this lecture here, the topic of degrees of freedom. If for for a planar linkage, what is the minimum number of links the minimum number of links which produce motion without the use of higher pair? That's a question that people always ask, because it's a design question. So there is, in a planar linkage, people can put together something and say, I can't, that's a linkage going to move, and I tell them it's not going to move because it does not fulfill the required minimum number of linkage in a planar thing, that's linkage that will cause the linkage to move. Like, for example, the answer is in fact 4, right? The answer is 4, but how to get it? So the answer is 4. Okay, right. Now, how to get that? For at least, before we get to the answer, I just want to say that if someone says, I have this linkage, no, it's not a linkage because it has 1, 2, 3 links. It doesn't have higher pair, just all lower pairs and links. So that's a structure. So I can use it to suspend something here, like if you're, I can use it to have some mess hanging or whatever like that. There's not a linkage, right? So if you want to make this a linkage, then you have to have the fourth element here, right? So they have 2, 3, 4, right? 1. So That's a linkage because the minimum number is linkage, right? Now, how to calculate this number 4? Okay, so you'll find that usually because the equation is like that in space, it's 3 in the plane, n minus 1 minus 2 r minus 2p, right? I'm going to say 3n minus 1 minus 2 r plus p and call them joints, like lower pairs if you like, okay? And because they have the same effect, and you'll find that in a simple linkage, because now I'm talking about minimum, so I'm talking about a simple linkage, you'll find that the joints, so I'm going to write this equation, 3n minus 1 minus 2g joints, just call them j for now. So you'll find in a simple linkage, j is equal to n, right? Like for example, this case here, r plus p is equal to 4, n is equal to 4, right? So another case here, right, do something here, fold by chain, right? R is equal to 4, n is equal to 4, right? So that's now that this is the why I said j is equal to n. So now the equation becomes f is equal 3, n minus 1 minus 2n, right? If I expand this slightly, I'll get n minus 1 is equal to f. Now, because I'm talking about the simple mechanism, because we are talking about the minimum, right, linkage, f is equal to 1, right? F is equal to 1. So my equation now is 1. Yeah, I just forgot. This should be minus 3, right? Should be minus 3 because 3 times n and that's 3n minus 3, right? Okay, so this should be 3. So the f now, so the equation should be 1 is equal to n minus 3, which gives me n is equal to 4. Right, so this is the simplest linkage in a plane, cannot have any less than 4 links at all if I don't have higher pairs. But if we had higher pairs, h, I can have whatever. Like, so, like example we worked on previously. So here, n was equal to 3, right? Because we had a higher pair due to h. All right. Okay. So now we come to the end of this specific topic, which is degrees of freedom in linkages. And in the next lecture, we'll start looking at the four-body chain geometric aspect of that and the indices of merit or the figures which determine the performance of such a linkage. All right. Take it easy and try to solve as many problems as possible. If you get stuck, please drop us a line on Moodle or by email or whatever. We'll be happy to help. Thank you.